Before we can spend hours and hours together working on our switches and routers, we need to spend a little bit of time with the cables that make our network possible. Because if we don't have the cables in the right place or the right cables in the right place, then we don't have any communication between our routers and switches. We're also going to spend a little bit of time with some Ethernet standards as well. Good stuff to know for your exam and for the field as well. Because whether we're talking about a host to switch connection, as we are at the top of the screen, switch to switch at the bottom, or a switch to router connection, we're using Ethernet and Ethernet-based cables to make that layer 1 connection happen. Just a word there about the layer 1 connection I mentioned. Some people say Ethernet runs strictly at layer 2 of the OSI model. Others say 1 and 2. That's kind of the camp I fall into. Do not stress about this for your exam. I see people on the internet just going insane about which one it is. Don't worry about it. What you need to know about Ethernet is the addressing, which we'll definitely be going over in another section, and also the standards that you're going to see here in this particular section. We're going to look at some of those Ethernet standards. We're going to look at a couple of very important cable types. And just a word, if you're totally new to this part of networking, Ethernet is really an umbrella term at this point because we have Ethernet, we have fast Ethernet, we have gig Ethernet, we have 10 gig Ethernet. And when someone says Ethernet, they're not just referring to the first standard I mentioned. They're really referring to all of these. Before we get to the cable types though, let's talk a bit about the wires inside those cables. Most of today's Ethernet cables are unshielded twisted pair, UTP, where the wires inside are pairs of twisted copper cables. There are 4 pairs, 8 wires overall. Now, of course, the first question is, why the twisted pair? Well, twisting the cables minimizes the effect of EMI, electromagnetic interference, from outside sources ranging from other cables to other wires in the same cable to actually elevators, believe it or not. And that twisting also lessens the amount of EMI that the wires are putting out. So it's stopping or at least minimizing the effect of EMI coming in and also preventing as much of it as we can from going out. And speaking of the elevator thing, I know that sounds funny if you haven't used it, if you haven't lived through it, I should say. But the very first network admin job I had, a lot of the cables had been run next to the elevator shaft, and they had not been able to figure out every day at lunchtime and quitting time why the network slowed down. We figured it out. I figured it out once I got there. At least I helped. We can also run into EMI problems, as I mentioned, from wires in the same cable, because this is not the first time or the only time you'll see this phrase crossing over. Crosstalk happens when a signal crosses over from one pair of wires to another in the same cable, and it has the unfortunate result of making the signals in both pair of wires totally unusable. So obviously something we want to avoid. Well, the second question I had, now that we've answered the twisted pair question, second question was, well, if it's unshielded twisted pair, why don't we have a shield on it? Does that mean that there's a shielded twisted pair option? And there is. Now, the shielding in STP, there's plenty of it because the shielding is wrapped around each individual wire first. Then additional shielding is wrapped around each pair of those same wires. Hey, this sounds great. I mean, how could we not love that? Well, STP is great in theory, but as we know, reality is not always as great as we would like it to be. It's so easy to damage the shielding on STP cabling, especially if you're handling it even semi-regularly, if somebody's moving it, if you bend it, you're actually causing more trouble than it's worth because you're introducing additional EMI even with slight damage. And it is very easily damaged. I've lived through that as well. STP costs more too. So it happens, your boss sees, well, what about these cheaper cables? Well, they last longer, everything. Oh, let's buy those. So for these reasons, unless you are in a particular area of a building where there's a tremendous amount of EMI, a particular device, an industrial device giving it off, you're not going to bump into a lot of STP these days. And another real world note here, every CCNA candidate, when they hear STP, ought to be thinking of spanning tree protocol anyway. And if you don't even know what that is yet, that's fine. We're going to fix that a few sections from now. But on your exam, whenever STP is mentioned, they're talking about spanning tree protocol unless the question is absolutely talking about some kind of cable. But I don't even expect you to see shielded twisted pair on your exam. It's that rare today. Now we leave behind problems like that when we move to fiber optic cabling. Just talking about moving to fiber optic cabling makes me happy because that kind of cabling has glass fibers in it that allows for much greater transmission speeds and much greater maximum cable lengths. So with those advantages, you know there's a reason that it's not everywhere yet, and there is, and that's simply cost. You know, fiber optic implementation is very expensive, and the fiber optic cable itself is still much more expensive than buying copper cables. We're going to talk about these Ethernet standards here for a few minutes, and I'm going to give you the official IEEE name for them and the name that regular people use for them, network admins, you and I. And I want to mention all the copper standards we talk about on the next couple of screens. They have a maximum cable length of 100 meters. This is good stuff to know for the field, and I would be astonished if in some way this didn't come into play on your exam. Now those copper-based standards, Ethernet, regular Ethernet runs at 10 meg. And the official standard is 802.3. You can tell it was the original because it doesn't have any letters on the end of it. It's commonly known as 10 base T. And if you are talking about Ethernet standards with someone in the industry, they're probably not going to say 802.3. They'll probably say 10 base T. That's why I'm giving you both names. Now, Ethernet uses 2 of the 4 pair of wires that are available. Then came fast Ethernet, and we thought we had achieved nirvana, clocking in at 100 meg. And the IEEE standard is 802.3U. You can remember that by U standing for unbelievably fast, which is something I made up, but it still works to remember it. And you and I call it 100 base T. It also uses only 2 pair of wires out of the 4 available. So now you're thinking, wouldn't it be a good idea if we had a way to use all the wires in there? Well, we didn't have the technology to do that originally, but now we do, and that allows gigabit Ethernet to exist, 100 meg speed. Now we're getting somewhere. This is 1000 base T if you and I are just chatting across the table, but the IEEE official standard is 802.3AB. The speed is possible in part because all 4 pair of wires in the cable are used. We're going to revisit Gig Ethernet in a few minutes, and you'll see some other reasons, or a big reason, that that speed is possible. You certainly won't be surprised to learn that the aptly named 10 gig Ethernet runs at 10 gigabits per second. We call it 10G base T. The IEEE calls it 802.3AN. Watch that G, and I'm even pointing to it on the screen as I'm recording this because it's really easy to gloss that over in an exam question. So if they're talking gig Ethernet, 10 gig Ethernet, make sure you see or don't see that G. Now, let's see. That fiber optic standard, fiber standards jump right to gig Ethernet. And the network admins, we would call that 1000 base LX. That LX is a tip-off you're talking about fiber. And the official IEEE standard for that is 802.3Z. That Z could stand for Zoom if you wanted to remember it that way. Now, why do we need these standards to begin with? Ethernet standards, of course. Well, when an Ethernet standard goes from point A to point B, whether that's in a test network or whether it's in a campus network, there's an excellent chance that the frame is going to travel over links with different capacities and capabilities. And here, very simple network, something you'd find in a lab. And we got a couple of 10 meg links and we got a 100 meg link. And Ethernet handles this beautifully. There's no problem at all. Because if the switches had to do some kind of translation every time a frame went from a link with one Ethernet standard to a link using another Ethernet standard, I mean, let's look at that. That would be a lot of translation, a lot of it. But thankfully, we don't have to do that. And by the way, that would be a lot of extra work for the switches, and of course it would slow the transmission down as a whole. And the reason no such translation is necessary is that all of those Ethernet standards use the same frame format, and that is about as simple as it gets. You got your data in the middle, you got your header out front, you got your trailer out back, bada bing, bada boom, you got your Ethernet frame. It's just that simple. So, we're going to talk about crossover and straight through cabling at the beginning of the next video because we got 3 connections here, but we need 2 different cables to make it work. I've got some excellent real-world notes for you here as well that I've lived through, and we'll go for that on the next vid.